Hi everyone. Today we're going to study independent events. What are independent events? Whenever the probability of an event E is not affected by the occurrence of another event F and vice versa, we say that the two events E and F are independent. If the events are not independent, then they are dependent. This is the formal definition of independent events. Two events E and F are independent if and only if at least one of the following two conditions is true. Number one, the conditional probability of E given F equals the probability of E. Or number two, the conditional probability of F given E equals the probability of F. Take note, two events E and F are independent if and only if the probability of E intersect F equals the probability of E times the probability of F. Let us see some examples. Example 1. Given the conditional probability of B given A equals 0.4. If A and B are independent, find the probability of B. For our solution, if A and B are independent, then by definition, the conditional probability of B given A equals the probability of B. Therefore, the probability of B equals that same value, 0.4. This is our final answer. Example 2. A coin is tossed 3 times and the events E, F, and G are defined as follows. For event E, the coin shows a head on the first toss. Event F, at least 2 heads appear. Event G, heads appear in 2 successive tosses. Determine whether the following events are independent. Letter A, events E and F. Letter B, events F and G. Letter C, events E and G. For our solution, first we're going to list the sample space, the events, their intersections, and the corresponding probabilities. Starting with the sample space. There are 8 possibilities in the sample space, and these are first HHH and HHT, then HTH, followed by HTT, and then THH. Next is THT, then TTH, and the last is TTT, followed by the event E, and the elements are H, HH, HHT, HTH, and the last HTT. The probability of E equals 4 over 8. We write here 4 because there are 4 possibilities in the event E. And the denominator is 8 because there are 8 possibilities in the sample space. We can reduce this to lowest term, so 4 over 8 equals 1/2. Next is event F, and the possibilities are HHH, then HHT, followed by HTH, and the last is THH. For the probability of F, this is equal to 4 over 8. In the numerator, we have 4 because there are 4 elements in our event F. Again, our denominator is the number of sample points in our sample space. So 4 over 8 is also equal to 1/2. Then the event G, and the elements are HHT and THH. For the probability of G, we have 2 over 8. We write here 2 because there are 2 elements in our event G. Number 8 is here because there are 8 elements in our sample space. The 2 over 8 is equal to 1/4. Then we will continue with our E intersect F, and we have 3 elements for that. For the probability of this E intersect F, this is equal to 3 over 8. There are 3 elements in our E intersect F, so we write here 3. And number 8 is again coming from the number of elements in the sample space. Next is the intersection F intersect G. We have 2 elements here. So the probability of F intersect G equals 2 over 8. And 2 over 8 is simplified into 1 over 4. And then the E intersect G, there is only one element, and that is the HHT. And the probability of E intersect G equals 1 over 8. Now, let us solve for letter A. So we write here, for these events E and F to be independent, we must satisfy this equation, that P of E intersect F is equal to the P of E times the P of F. Let us get the corresponding values from this side. So we will have 3 over 8 for this P of E intersect F. And we can see that this is not equal to the product of P of E times the P of F, because 1/2 times 1/2 will give us 1/4, and it is not equal to 3 over 8. Therefore, E and F are not independent. So let us write the remarks opposite letter A. Let us solve for letter B. F and G will be independent if it satisfies this equation. P of the F intersect G equals P of F times the P of G. Again, let us get the corresponding probabilities from these values. So we have the P of F intersect G is 1/4, and this is not equal to the P of F, and that is 1/2 times the P of G is 1/4. So when we get this product, it will have the 1/8, which is not equal to 1/4. So we may say now that this F and G again are not independent. Let us write our remarks opposite letter B. Let us now solve for letter C. We now look at this equation to prove whether E and G are independent. Let us substitute the values, so the P of E intersect G will be 1/8, and this will be equal to the P of E, which is 1/2, times the P of G, and that is 1/4, and the product of 1/2 and 1/4 is 1/8, which is equal to our left side. So we say that the events E and G are independent. So let us write our remarks opposite problem C. So this is now our final answer. Today we're going to study conditional probability. What is conditional probability? Whenever we are finding the probability of an event E under the condition that another event F has happened, we are finding conditional probability. This is the symbol that is used for conditional probability, and this is read as the probability of E given F. It denotes the problem of finding the probability of E given that F has occurred. This is the formula to be used. The probability of E given F equals this fraction, where the numerator is the probability of E intersect F, over the denominator, and this is the probability of F. Let us see some examples. This is example 1. A single die is rolled. Find the conditional probability of obtaining an even number given that a number greater than 3 has shown. First, let us assign E to be the event that even number shows. Let F be the event that number greater than 3 shows. So we are looking for the conditional probability of E given F. Let us list event E, and these are 2, 4, and 6. And the elements of event F equals 4, 5, and 6. We know that the sample space has 6 elements. Now, for the E intersect F, there are two elements, and these are 4 and 6. Therefore, the probability of F equals 3 over 6. We write here 3 because there are 3 elements for F. And we write here 6 because there are 6 elements in our sample space of rolling a die. Next, the probability of E intersect F, and this is equal to 2 over 6. We write here 2 because there are 2 elements in the E intersect F. Again, we write 6 in the denominator because there are 6 elements in the sample space. Now we write our formula and we will do the substitution. In our numerator, the P of E intersect F is 2 over 6, and in the denominator, the P of F is 3 over 6. Then let us write this complex fraction into 2 over 6 times 6 over 3. And then we can cancel the 6 and the 6, and our final answer will be 2 over 3. This is now the conditional probability required by the problem. Let us have example 2. Given P of E equals 0.5, P of F equals 0.7, and P of E intersect F equals 0.3. Find the following. Letter A, P of E given F, and letter B, P of F given E. Let's begin with our A. Our formula will be like this, and we will do the substitution coming from the given. So we have now 0.3, that is the P of E intersect F, over P of F is 0.7. We will simplify this fraction, and this is equal to 3 over 7. Now for letter B, we have P of F given E, and this is equal to P of F intersect E over P of E. Let us do the substitution now. This P of F intersect E is just the same with our P of E intersect F. So we will use this value 0.3 here over the P of E, that is the 0.5. Let us simplify this. This is the same with 3 over 5. These are our final answers. Let's have example 3. Given two mutually exclusive events, E and F, such that P of E equals 0.4, P of F equals 0.9, find P of E given F. For our solution, since E and F are mutually exclusive, it means the P of E intersect F equals 0. Now, using our formula to find the conditional probability P of E given F, we will substitute the values 0 in the numerator over the P of f is the 0.9, and the answer is 0. This is our final answer. Example 4. Given P of f given E equals 0.5 and P of E intersect f equals 0.3, find P of E. For our solution, let us first write the formula that P of f given E equals P of f intersect E in our numerator over the denominator P of E. And then let us substitute the corresponding values. So we have now 0.5 equals 0.3 over P of E. In this equation, we can now solve for P of E. Let us simply interchange the position of this 0.5 and the denominator P of E. So we have now P of E equals 0.3 over 0.5. Then we can now solve for the P of E. This is equal to 3 over 5. This is our final answer. Let us have example 5. In a family of 3 children, find the conditional probability of having 2 boys and a girl, given that the family has at least 2 boys. For our solution, first let us assign E equals the family has 2 boys and a girl, and F equals the family has at least 2 boys. Then we take note that we want to get the P of E given F. We list now the sample space along with the events E and F. For our sample space, we have here 1, 2, 3, 4, 5, 6, 7, 8 sample points. Then for our E, we have 3 elements, and these are BBG, BGB, and GBB. For event F, we have 4 sample points, and these are BBB, BBG, BGB, and GBB. We can see that the E intersect F has 3 elements, and these are BBG, BGB, and GBB. Now, we can notice that P of F equals 4 over 8. We write here 4 because there are 4 elements in our event F. And in our denominator is 8 because there are 8 elements in the sample space. And the P of E intersect F equals 3 over 8. We write here 3 because there are 3 elements in our E intersect F. Over 8 because again there are 8 elements in the sample space. Writing our formula now, and let us do the substitution. So we have now this P of E intersect F is 3 over 8 over the P of F is 4 over 8. For this complex fraction, we may write 3 over 8 times 8 over 4. Then we can cancel the 8 and the 8, and the final answer will be 3 over 4. This is our final answer. I hope you learned something from this video. See you again next time.